Welcome back, and this is our last lecture before the Easter break, and then we catch up again after the Easter break. So the plan for today is to give you first a summary of Boltzmann machines, which from last week's slides contain a pretty extensive derivation of some of the more typical Boltzmann machines. But I wanted to bring up the Boltzmann machines again with a kind of a 10-15 minute reminder in order to link that with variational autoencoders so that you can see the differences. And we are going to use variational autoencoders as a stepping stone towards the more, how to say, popular methods, which are called diffusion models. And then after that, which means that this will be in the beginning of May, we will talk about the general adversarial networks, or GANs. And then if we get some time, we will also discuss the mathematics of reinforcement learning, which again is based on you extracting a probability distributions, performing Markov chain simulations, etc. So much of that kind of basic machinery, which is now used in these type of models, are essentially going to be reused again and again. Now, one of the things I wanted to set up for you as well are some of the reading recommendations and links to codes. So if you look into the textbook by Babcock and Bally, you will find the Boltzmann machines, and you will also find more on Boltzmann machines, and these are in the lectures by Foster. You will find a discussion on many of these energy-based models where you replace the energy function with a neural network, for instance. So instead of having these simple cases, which we had in the lectures from last week, where you can use a binary or Gaussian binary machine, you replace this energy-related functions with, for instance, a neural network. So if you now look at the essential elements of these generative methods, it's actually us trying to train a probability distribution. And the methods which we are going to focus on within this kind of generative methods are what we might call some of the more popular ones. So today's lecture, I'm going to use the whiteboard quite a lot, essentially because I want to go a little bit more slowly through the basic mathematics, which also links with variational autoencoders. Variational autoencoders, they also had another name, and the name is variational Bayesian methods. And we are going to see a clear link between Bayes' theorem and the kind of theory which we're going to develop. So variational autoencoders have been very popular, but their popularity has been, replaced by diffusion models, which in a certain sense are chains of variational autoencoders. And we will come back to their links next week or after the break, and then the week thereafter, where we discuss diffusion models. So I'm going to switch to the whiteboard, if that's okay with everybody. And we're going to step a little bit slowly through the basic mathematics, which we need to set up. So if you think of these variational autoencoders and also link them with Boltzmann machines, basically what we want with generative methods is the following. So the basics, so let's just take a bird's view on this. Basics of generative models. So you have some data set, which is mapped into some region. So you have a data set. And this maps into the region. And this is our data set X. Then what we want, based on that data set, we are assuming that there is a probability distribution which describes the data. So this could be a Gaussian, it could be an exponential distribution, or any other type of distributions, and perhaps even some distribution which we don't know. Then what we want through these different processes is actually to produce some X tilde, which is governed by some distribution, P of X, with some parameters theta. So what is in between here is something we are going to put it with a question mark. And the reason why I bring this up is that I want to link this with Boltzmann machines and variational autoencoders so that you see clearly the difference between a Boltzmann machine and a variational autoencoder. Now, since we are calling this autoencoders, in some way, there must be some kind of similarity with autoencoders, which we discussed earlier. And there is some kind of similarity. So we're going to bring that back again when we start looking at the mathematics of variational autoencoders. So as the name says, when you deal with something which is variational, it means that you are trying to optimize something which can have a lower bound. So for those of you who are familiar with quantum mechanics, you may have heard about variational theory in quantum mechanics, which means that if you have the exact wave function and you calculate the expectation value of the energy, you should get the exact energy. If you don't have the exact energy, you will get a result which is larger or equal to the exact energy. So that means that there is some kind of lower bound which we are performing the optimization with respect to. And this is where you have the name variational. But let's now, since we mentioned Boltzmann machines, let's step back a little bit. So let's step back 2 weeks and start with the basics which we looked at. So what we want, if you now look at this function P of X, so we want, in these generative methods, we want to find a probability distribution of X in terms of some parameters theta. Now, ideally, this probability distribution here, where X now is a domain of events, so X may now contain all the events from X0, X1, up to some X of n minus 1. So that's the domain of events. Then the ansatz which we have made for the probability is that this probability P of X of theta is now a function of the individual probabilities, where these X of i's are now elements. So this is the domain of events, D. So these X of i's are in here. And then we have the individual probabilities, X of I of theta. So theta is a set of parameters which we want to optimize. This is what we are assuming in essentially all these models. So this means that the X's, which we have here, they are independent and identically distributed. That's a basic assumption which we're making. Now, this probability distribution depends also on some additional parameters. And this can represent what we call the latent space or the hidden space. So the probability P of X is what we call, or this X of I here. If we now break it down into that, this is what we in statistics call a marginal probability. And this marginal probability is now a sum over some additional quantities H of J, and I'm just leaving that unspecified. This has a domain of events itself. And this is now given by the probability of having X of I, H of J, and theta. So this H is something which we in the Boltzmann machine call the hidden layer, or the hidden variables. Alternatively, as you will see today, this is going to define the latent variables. So we are going to make, as we did with autoencoders, we are going to transform and reduce the dimensionality of the problem into a smaller space, which is called the latent space. And that latent space is one way by which we encode the original probability into a smaller space, as we did with autoencoders. And then there is a decoding part, which brings us back to the probability distribution, which we want to find. So this hidden layer gives us some additional flexibility. And if we now look at the a continuous distribution, if this P of X now consists of a continuous distribution, that means that this P of X of I of theta can then be written out as an integral over d of H, and H is now defined in its own domain here, and it is a probability where we now integrate away X of I, and then we have H, and as a function of theta. Now, when we then looked at Boltzmann machines, so let me quickly remind you of that. Then we made an assumption that this probability distribution, this P of X, and now I'm dropping this dependence on X of I. So I'm just writing a little x, so hopefully this can be distinguished from the uppercase X. So when you now look at this function here, this should be an uppercase letter X, and the small x's are the individual events. This quantity here is normally given in terms of some function of X of theta divided by the partition function of theta. And this partition function is a function, if we now assume that we are dealing with continuous variables, then it's a function where we integrate over d of X, and X is now belonging to a domain over continuous variables. We have H, which has its own domain, and then it contains now a integral where we integrate over both the X's and the H's with a given set of parameter theta. So this is what we call a normalization constant. And for those of you who have taken a course in statistical mechanics, this is called the partition function. So this was just to remind you of some of the things which we discussed earlier. So this is a normalization constant, and it's normally a quantity which is very difficult to calculate because it depends on many, many variables. So if you're looking into statistical mechanics, this is called the partition function because it's derived from all the way you can partition the degrees of freedom in a specific system. Okay, so for the RBMs, when we looked at them, this means that this probability distribution for an RBM, if we look at this quantity here, and we want to be a little bit more detailed, we could now rewrite this if we think of the total distribution. So P of uppercase letter X of theta is then going to be given by 1 over Z of theta, and then it's multiplied by these functions where we have an X of I elements in X of these functions X of I of theta, which again is going to be given by 1 over C of theta. And then what we have is now a product over the x's, X of I. And then we are going to have a sum over all the HJs. And then we have an F of X of I, H of J, and theta. And what we ended up doing then, when we were performing the calculations, is that we would take the log of this function. So we are going to optimize the log of the function and not the product. So we optimize log of P of X. So that means that we end up having to take the derivative with respect to theta of log of P of X. I hope you can see that this is the uppercase letter X, even though sometimes the X's can look like a lowercase x. So what we found then last week and the week before is that this function here is then given by del theta, and then I have an X, a sum over X of I elements in X, and then I have my log, and now I have summed away all the H's. So I have the log of this function minus the expectation value of and then we have log of the function f of x of I of theta. So that's an expectation value. Now for the different Boltzmann machines, a very typical one could be something like a binary Boltzmann machine. So let me quickly remind you of that. So this is a quantity which we have to calculate. And the second quantity, which you see here, this quantity which we can frame in here, is normally calculated with the Markov chain Monte Carlo methods. So we normally write this as MC squared, Markov chain Monte Carlo. And the typical sampling rule, which is being used to accept a new suggested position, is either the Metropolis algorithm or Gibbs sampling, or you can do Langevin sampling. These are very popular ways of performing the sampling. Now, Gibbs sampling is the most used one, and Gibbs sampling is based on Bayes' rule, and you have a recipe for doing that in the lecture notes from last week. So in the technicality here then is that we end up having to calculate an expectation value of a function which is a model which we have made. So till now, everything here is pretty generic. And when we now look at the specific models which we have, then if we look at these restricted Boltzmann machines, which we went through last week, the RBM is then given by a function. If I now look at this x of I of h of j as a function of theta, this is typically now given by some function e of a to the power of t times x plus b, so transposed, so not to the power of t, but transposed, plus x transposed times w of h. And these functions, which we have here, they are typically given by a set of parameters, which are called the weights and the biases. So this would be a sum over I equal 1 up to n, the number of visible nodes. And this plays the role of a bias, this a. So this is a parameter, plus a sum over the hidden nodes up to n. And then I have a bj and hj, plus a sum over I and j up to m and n. And then I have my x of I have the weights, and then multiplied with h of j. So a typical model is a binary. And in all these cases, as you can see from the slides from last week, then you can calculate analytical expressions for these functions f and the different probabilities which are needed to set up a Boltzmann machine. So x of I can take the value, when you say binary, could take the value 0, 1. And h of j could also take binary values like 0 and 1. And the parameters which we have to fit, these parameters a, the biases, and the w's, which are the weights, these are then setting up a collective container, theta, not theta optimal, because that's the one we want to find. So theta contains now these parameters a, b, and w. And w are the weights included in the model here. So a typical situation which you could find then would be something like this for a binary model. You have a visible layer. So the quantities which you see here are called the visible variables. And the h are the latent or hidden ones. And then there's a link between the latent and the hidden one, and the visible ones. So a neural network for a Boltzmann machine, and it's called a reduced Boltzmann machine because we have only one hidden layer and there is no contact between the nodes in a given hidden layer. That could be something like this. So you have a set of visible nodes, which we label as an x1, x2, up to some x of n minus 1. So these are the visible ones. These could be the pixels of an image. So if you want to train a Boltzmann machine, as you can see from the lecture notes from last week, there is an example where you train on the MNIST data. And the MNIST data, then the visible nodes would then represent the pixels of an image. Alternatively, if you're dealing with, let's say, the solution of a differential equation, like Schrödinger's equation, the x's could then represent the positions of a particle. So if you have 10 particles in 3 dimensions, you would need 30 visible nodes. 3 dimensions times 10 particles, that would specify exactly the positions of the particles, if that is what is needed. And then we have the hidden layer, where we would have a similar amount of variables. So this should be x, not xn, xn here. So we would have h1, h2, up to hm. And what we have here is then called the hidden layer. And later we are going to rename it as the latent layer, or the latent part only. So this is the hidden layer, or hidden nodes. And these are connected by the weights and the bar, and which we need to train. So we have the different weights, and et cetera, et cetera. And here we have the weights. So there is no connection between the nodes. You can make this deeper and deeper. So you can stack hidden layers on top of the first hidden layer. But then typically the model becomes much more difficult to train. Now, as I mentioned previously, these functions here, which you see here, this is normally called the energy function. This is often nowadays replaced by, let's say, a neural network or convolutional neural network. So generically, these energy-based models, they do not need to be limited to these simple cases. Now, the nice thing with these simple cases, as you can see from the lecture notes from last week, is that if you take a binary, or if you let x be continuous and replace a binary with a Gaussian binary, then you can calculate the different probabilities which you need in these expressions, like this function here. You can have analytical expressions for them. And that makes often the numerics much easier, because you have simple exponential functions. And in the lecture notes from last week, you will see all these kind of exciting derivations of these different probabilities which you need. So we are not going to discuss that in more detail than what you see from the previous week. So nowadays, when you use JAX and automatic differentiation, it's actually much easier to replace this function here with a complicated neural network. But the neural network, as you see in this function, is the one which we have represented here. So that specific function with its parameters, which are trained by using standard gradient descent, stochastic gradient descent, etc. And then you would have Monte Carlo sampling, is typically what you end up doing when you train a Boltzmann machine. Okay, so that was one of the things which we went through and which was contained in last week's material. What I want to do now is to switch back a little bit to autoencoders and use that as a stepping stone towards the discussion of variational autoencoders. So let me give you a quick reminder on autoencoders before we move on here. So this is something which we went through in the 8th and the 9th week, and you can find all the information in previous lecture notes. So there's a reminder on autoencoders. So a typical autoencoder, as we have seen it, is something where we now feed in some data. So we could feed in some data X. So this is the input layer. This can now be decoded or encoded. And we have some function which we called for f. So there's a function f which takes x, and this can have its own parameters, phi. So this is what we call the decoder part. No, sorry, not the decoder, but the encoder. This produces an output which we call the latent space. So it produces an output which we call H. H is given by this function f of x of phi. And this f of x could be a neural network. Then we do reconstruct this data which we had. So there's a decoder part. And then we can define a new function, which we can call g of h. So this depends on h then. And this has some parameters which we can call for theta. And this produces a final output x tilde. So x tilde is just g of h of a new set of variables theta. So these could be different types of neural networks here. And you could now think of something like this if you want to give a specific example. So, by the way, before we do that, we would then define what is called the reconstruction error. And we want to optimize that one. And that means that we are going to find the optimal parameters of theta and phi, which could be the parameters of a neural network, in the encoder part and in the decoder part, as we saw in the lectures. And the typical function which we would then optimize could be something like the mean squared value. So we would have the norm of x minus x tilde, and this is the norm 2 of this quantity here. Well, now this x tilde is given by this decoder function. So if you want to bring up this as a, in terms of a typical example, what you could have then is the following. So you could think of you having some input. Suppose that this x, input x, suppose it has 784 units. So these are the data sets which we feed in. Now then, there is an encoder part which reduces this to, let's say, 100 units. And then finally, this is reduced down to 20. So this is the latent space. So the latent space is a considerable reduction of the dimensionality. So this is the encoder. And this is the latent space. And then what we do next is that we try to rebuild this. So we could again have 100 units, but we don't need that. We may not have 100 units only. So the decoder part is the one which encompasses these pieces. And then we have the decoder part, where we then build up the final data set again, which is 784 units. So this is now the decoder part. And the reconstruction, which is done, is so that this x tilde, which we can put in here, so that's the x tilde, which is the output. And then we optimize the reconstruction error as a way to find the optimal parameters. This is the essence of an autoencoder. Now, there are some drawbacks with autoencoders. I mean, they are extremely popular and they're very useful. So if you also think back to what we discussed in connection with the principal component analysis. So in the principal component analysis, what we did was actually to perform a singular value decomposition. So you could think of an image here which has 784 pixels, and you reduce that image down to 20 pixels. This is the latent space, which is your dimensionality reduction. And you could use that latent space as a space where you save the specific data in a reduced format. In a principal component analysis, when you use a singular value decomposition, what happens then is that you have the orthogonal vectors of a singular value decomposition, which allow you to encode this dimensionality. Then, since you have these eigenvectors or orthogonal vectors, you can then reconstruct it, which is the reconstruction here. And you can reconstruct an image which has the same dimensionality as the one you started with. So the principal component analysis and singular value decomposition are ways by which you can reduce the dimensionality, and where you have a simple linear algebra interpretation of the results. But when you use an autoencoder, what you're in principle doing then is that you can think of you producing just some few outputs of a neural network, starting with many, many more data here. And that's a way to reduce the dimensionality of the problem. Okay, so there are some drawbacks. So they are very popular. So the limitations of the, if we just list some of them, of autoencoders, AEs. So one obvious limitation is that it's not generative. So that means that in general, unless we are producing a solution which is a probability distribution, then a model like this one is that they don't define a probability distribution. Define a distribution. So the whole thing with generative methods is that we want to define a probability distribution. So that's one of the limitations. The other one, which may not be seen as a limitation, but is something which is always critical, that is, how do we choose the latent dimension? How to choose the latent dimension. So the thing which we want to actually, with variational autoencoders, then we want to find, we want to have a generative model that learns explicitly a low-dimensional representation. That's one of the things we want with a variational autoencoder. So why variational autoencoders? So these methods have the similarity with the Boltzmann machines, so the energy-based models, that we start with a probability distribution, but the way we obtain this probability distribution is different from what we did with Boltzmann machines. So one of the things we want to do now is to have, so, and this is one of the distinctions between a variational autoencoder and an autoencoder. A VE is actually a generative model. Let me just, is a generative model. Is a generative model. So we generate a probability distribution that knows explicitly, learns a low-dimensional representation, a low-dimensional representation. It does it explicitly. So this kind of a network is actually something which gives us now some kind of input, and it's going to allow us to predict a final probability distribution, where we also are able to train a reduction of the dimensionality in a so-called latent space. So the philosophy is going to be similar to what you see here, but now we are going to train probabilities. And the kind of quantities which we will be using are actually given in terms of Bayes' theorem, the marginal probabilities and conditional probabilities. So let me quickly remind you of some of these aspects, okay? So a quick reminder on statistics. So if you now look at the probability of, and let's now skip the parameters theta. Skip theta, phi, etc. And let's just do this a little bit simpler. So how do we actually choose this latent dimension? How do we generate these probabilities? And in order to do that, let's now look at a general probability. And this is the so-called product rule. So we have X and this latent space. So that's the probability of X and the latent space. Okay. And this is given by the probability of X. This is the conditional probability given H multiplied with P of H. So P of H is the probability of just H. Now, the probability of P of X, this is also equal to P of H of X multiplied with P of X. And then we can combine these and find a Bayes theorem. So let me quickly remind you. So this P of X then is actually the quantity we are looking after. So we want to train such a probability where we have integrated away the latent space. So this will be an integral over our conditional probability multiplied with the probability for having P of H. So this is what we call a conditional probability. Conditional prob. This quantity which you now see here, this one and that one, they are called marginal probabilities. And it's called marginal because we have integrated away all the other degrees of freedom. And we are then just left with one degree of freedom, which is either X or H. And you see the formula for, if this is a continuous distribution, this will then be the formula for the marginal probability. Then another quantity which we end up with then is something which is called Bayes' theorem. And actually, if these quantities are given by discrete probabilities, so in case of discrete probabilities, probs, then what we would have is that this P of X of I is then given by a sum over all the HJs. And then I have my P of XI given HJ multiplied with P of HJ. And alternatively, if I look at the P of H of J, and we use this in the derivation of the probabilities for the Boltzmann machines, then we have a P of HJ of XI and P of X of I. Now, when we are going to do the training, we need actually to have a model for these probabilities. Okay, and then let me also quickly restate Bayes' theorem. That combines the product rules which we have, and that gives us something which is called the posterior probability of X of H, which is then given by P of H of X multiplied with P of H, P of X, and this is divided by the marginal probability for H, which is then given by the sum over Xi's, and then I have a P of X, HJ, or H, let's just put it like H, of X of I, the conditional probabilities, multiplied with P of X of I. And then you can change it with H of X. And we had some examples 2 weeks ago where we discussed the relevance of Bayes' theorem in estimating data on results from, let's say, a mammography. So this is normally called the posterior probability. The quantity you see here is just called the likelihood. And we need to have a model for these, likelihood. And the quantity you see here is normally called the prior. And you need a model for that one as well. So if now this P of X is given by a uniform distribution, and this likelihood here, or conditional probability, is given by a Gaussian, then the final probability will be a Gaussian multiplied with a constant, which is given by the prior. So if you have simple probabilities, like a Gaussian multiplied with a uniform distribution, then the final distribution becomes a Gaussian. So this is extremely, is a theorem which is widely used in this kind of manipulations, which we are going to see now. So what we want now is to just look at some of the basic equations which we are going to set up here. So the quantity we want to optimize is the following. We want to optimize this is log of P of X. So in principle, what this is, it's actually log, but I'm going to skip now in the notation now, I'm going to skip theta, just for simplicity, okay? So in order to not have too much clutter in the equations. Then after the break, we are going to bring in all the parameters, because then we are going to set up the model for the variational autoencoder. Okay? Any questions so far? Does it sound okay? If I just skip this parameter theta? So what we are going to do then, when you look at this quantity, is that this is equal to log, and let's just write it down here. So we will have an integral over P of H, and then it's multiplied with the marginal probability. No, sorry, the conditional probability of P of H of D of H. So this quantity here is nothing but log of P of X of H of D of H. And we are integrating away one of the degrees of freedom. And just remember now that this one, when we use the product rule, is the same as P of X given H multiplied with this probability P of H. So this is the product rule in statistics. Now, the next thing we're going to do now is to insert 1. And 1 is going to be equal to Q of H, which is, as you will see after the break, is going to play the role of the encoder. So when we are setting up variational encoders, this is now the one which we will call later for the encoder. Now, this part here, this one, is going to be our decoder. So this Q of H is now going to represent the degrees of freedom. So we are not going to get, this is not the encoder, but with the encoder, we are going to find Q, and that represents the latent space. So this is going to be the latent space probability. So that means that starting from the latent space, we have now assumed that we have constructed this Q of H with the latent space multiplying with the conditional probability, we can then find the final probability P of X. So P of X is the model which we want to find. And if we go back to the very beginning of the lecture today, if you now look back at the one of the first images which we made here, this one, this P of X is the one which we want to find. Then there's some data set which we feed in. This is now decoded and it's sent into a latent space. And then from the latent space, we are going to find the final probability. So if I now add a little bit here, so there's going to be here a latent space, latent, with a function Q of H, which then will lead to a P of H. And this P of X of theta will then be given by this integral where we integrate away these degrees of freedom, P of H, and multiply that with a conditional probability like this. And this P of X, which you see here, this one, is the one now which we are going to optimize so that this X tilde, which will be generated by this one, gives us a reconstruction or a difference between the original data X and the generated data X tilde, which is as small as possible. That is the reconstruction error. Okay. So this is a kind of a little bit overarching philosophy. So let me be a little bit more explicit. Now, in the first derivation, I actually wanted to leave out the dependence on theta and phi, but the kind of model which we will look at the very end for the variational autoencoder, and then we're going to take a small break. So the VIE is going to look like something like this. So we had this data set with our X here. So we send in a data set, which is sent in here. Then there will be a parameter or parameters theta. Sorry, not theta, but phi. And we are going to construct a new probability, which we are going to call Q of phi, where we have H given X. So X is the input. This is the encoder. This one maps over to the latent space. And this is where we perform the dimensionality reduction. So this latent space now gives us a degree of freedom H, which has a given defined by specific dimensionality. It has a probability P of theta of H. So we define a probability which now represents the reduced dimensionality. And we want to find this latent space through optimization. Then there is a decoder part. And in this decoder part, what we find then is the probability as a function of a parameter theta of making a transition from X to H. And we have a new parameter or set of parameters, parameter theta. This gives me now P of theta of X. This is the quantity I want to have at the end. And that one is now used to generate, so my X tilde, when we put this sign here, it means that X tilde is generated by this function here. And that is the one which we feed in here, X tilde. And then we want to optimize the difference between X and X tilde. So if you think of the name autoencoders, this is reminiscent of an autoencoder, but it's not an autoencoder because we are going to manipulate these integrals in order to find a lower bound, which we will vary the parameters with respect to. That's the name variational. But we are going to have a probability here, which now encodes the data. It reduces the dimensionality into a smaller space, and then we re-decode it and bring it back the full value. So that means that if we can train such a probability distribution, we can use that one to generate new data. We can generate new images if we want to. And we will also have, since we have a probability, we will have an estimate on the error we make because we can calculate standard deviation. And that is an advantage compared with, let's say, you training an autoencoder. Because when you have an autoencoder, you may not be able to get an estimate on the error of the parameters which you're fitting. So this is one of the benefits of actually fitting a probability distribution. So after the break, we are going to go through some of the mathematical details, and you're going to encounter not one of my relatives, but it's called the Jensen's inequality. And that is an inequality which is used in this type of calculations. So let's take a small break. I wanted to give you a kind of general view, And then after the break, we are going to set up the mathematical recipe for performing these calculations. And after the Easter break, we are going to look at how we can encode it. And these kind of, if you now think of diffusion models, these variational autoencoders are actually building stones in a diffusion model. But then you're going to have many such small latent spaces. That's going to be the big difference between a variational encoder and a diffusion model. So welcome back. And what I wanted now is to take a simpler case where I ignore a little bit this part here. And then I'm simply going to look at the connection between the latent space, the decoder, and then the final production of these X's. So if you look back a little bit to what we did here, we introduced a function Q here, which in this simpler case is going to play the same role as what I called P theta here. And I have suppressed, in this simple example, I have suppressed these different parameters which we are going to vary. Okay, so the model which we started looking at was something which looks like this. So we looked at the optimization of log P of X. And this is the same as log of P of H. And then this is multiplied with the conditional probability and then integrated over all the degrees of freedom H. So this is an integral, and we just put it like this because it's a log of that quantity. And then what we are going to do in here is just to insert 1. And we are going to insert that as Q of H, which is now going to be a model for my latent space, but I have just left it unspecified here. Now, there is something which is called Jensen's inequality. So as I said before the break, this is not one of my relatives. Inequality, not equality, but inequality. And this deals with properties of convex or concave function. So in our case, we are assuming, since we are taking log P of X, that this is a concave function. It's not a convex function. So that means that what we have then is that this is going to be larger or equal than an integral over Q of H. And then I have log, and then I have my P of H divided by this function Q of H, multiplied with P of X of H, and then D of H. So this is called Jensen's inequality. Now I can split this, since I have a log here, in 2 terms. So one term is now going to be given by Q of H, and then I have log of P of H divided by Q of H. And you see now that this one looks like an expectation value because I have a probability Q. So Q plays the role of a probability. So Q is a probability. I forgot to mention that. All the quantities which we have in the as integrants are actually probabilities. And when I write it like this, you see now that this looks like a probability times a function we are calculating the expectation value of. So that's the first term. And then if we look at the second term, that goes like, if we take that one, this is Q of H times log of P of X given H, and an integral over D of H. So both of these expressions look like probabilities. And I can rewrite that as a probability where H, and this symbol which you see here now means that H is given by a probability Q. So this one means that H, when we generate it, it's given by a probability Q of H. As we had X is proportional to the probability, is given by a probability P of X. So think of this like a Gaussian. If you look at a Gaussian distribution, if you're a little bit unfamiliar with this notation, you would say that if X follows a Gaussian distribution like this, and then you could have some mean value, mu of X, and then some sigma of X. That would be one way of writing that X can be generated by a normal distribution with a mean value, mu of X, and a standard deviation, sigma of X. That's a kind of standard notation in statistics. So what this is, so this E is an expectation value, and then the first expectation value is simply the log of P of H divided by Q of H. That's the first term. And then the second term, so let's just put this in parentheses because this is a smaller side. Then there is a plus, and then I have an expectation value of H given Q here, and this is given by log of P of X given H. Later, we will rewrite this in terms of the parameters so that you see that we're going to have a set of integrals which we're going to optimize. But let's stay with this simple model because we can do something easy here in order to visualize what is going on. So if you now look at the, let's say we take the term, or the second term here, let's look at that one. So if you now, so let us look at the second term. Let's look at the second term first. Because this will prepare us a little bit for how we are going to do the variational autoencoders. So what we could do now is to assume the following. So assume, so, and this is actually not so different from what we're going to do, because in order to be able to perform these calculations, which you see here, these beautiful calculations, we need to make an assumption about the probabilities. And this is also the same thing which happens when we set up diffusion models. So the assumption which is often made is that of a normal distribution. So that means that we could now assume that log of this P of X given H is simply given by the log of a normal distribution of N. It is a function of X, and then there is a function G of parameters theta of H, and then there is a standard deviation sigma. So if we do that, what we would have then would be something like this. So this is log of, and if we plug in the standard definition of the Gaussian distribution, we would have the standard deviation here. And then depending on the dimensionality, D, so this is the dimensionality of the system. If it's in 3 dimension, it's 3. And then we have multiplied with the exponential, and then we have minus 1 divided by 2 sigma squared, I think it's squared. And then we have X minus, and this is a norm 2 of G of this theta of H. And this is squared, it's a norm 2 squared divided by, and this is the exponential here. And when we take the exponential, this gives us minus 1 over 2 over sigma and sigma squared. And then I have times X minus G of theta of H squared plus a constant. Now, if you think back to what we did with autoencoders, so think just a little bit back. So think back to autoencoders. Autoencoders. Then what we had is that X tilde, what the model is making, would be given by this G times some as a function of some parameter theta and as function of h. So what you have then is that this quantity you see here, which will be part of the optimization now. So this quantity is nothing but the reconstruction error. So this is the reconstruction error. So let's try to see that. So if you're thinking of autoencoders, if we make this simple model, which you see here, then we could interpret this function, the second term, which we have in this integral. So that means this term here. We can then interpret that one as us optimizing the reconstruction error. But there is more to the picture than meets the eye, because we have this term as well, which needs to be included. So when we are performing the calculations now, we will have one term which we have seen before. So if we loop back to what we said in the beginning of the previous lectures when we reminded ourselves about autoencoders, then I call this function for g, h of theta, the parameters. And this is the one which I use to decode from the latent space and produce a final output x tilde. And this x tilde is nothing but this function here. And this g, which you see here, plays the same role as this function g, which I plugged in here, which I have left unspecified. Okay? So if I set this up with that as an example for the probability here, then I end up with a term which I can call the reconstruction error. And you will often see that since you end up, in most cases, using a Gaussian distribution as a model, then you will see that this term is being called the reconstruction error. Now, the first term, however, which we had, is something which we can actually give an interpretation to. So what about the first term? So let's put numbers on them. So we put this as a term 1, and this is our term 2. So the question now is, what about the first term? Now, the first term leads us to something which we have not defined yet. So let's do a small intermezzo here. So a small aside. And this intermezzo is actually called the Kullback-Leibler divergence. So let's define that one. Because this is a quantity which is widely used in these types of calculation, and it's a metric of the quality of your distribution. So it is defined as follows. So KL, Kullback-Leibler, you will see it defined like this, P with respect to Q. You will also see it in the literature like this as a function D. And this is a function of a probability P and a probability Q. And it's typically defined as, so sometimes people put a negative sign in front of it. So this is given by a probability P of X. And now we are integrating over the domain of possible X values. And it's given by log of P of X, of D of X, of dx. Now, this quantity, which you see here, is nothing but the expectation value of X given by this probability P of log P of X, no, not D of X, Q of X, sorry, of Q of X. And this is the same as the function which we put up in the first term. So if you look back at your notes, you will see that this term here is nothing. So statistically, this is an expectation value. And the way you can think of this now is that this P of X is the probability which describes your data. which you in principle don't know, but suppose you have a probability distribution which is known, which describes your data. Then Q could be your model for the data, which we have been discussing till now. So clearly, if you are lucky and you find a Q which is exactly equal to P of X, then this quantity is 1, and you have log of 1. And then the Kullback-Leibler divergence is equal to 0. So it's a kind of metric, although it doesn't fulfill the kind of standard axioms for being a metric. It's a kind of metric on how far away you are from the true distribution. So suppose now, just as an aside here, so this is an aside. So you can suppose that, suppose f P of X is a true distribution, the real distribution, real probability, prob distribution. And Q is the model you make, is a model. Then you see that this KL of this DL of the P of Q is equal to 0 when P of X is equal to Q of X. There's also another thing which is worth looking at. When P of X tends to 0, so when P of X tends to 0, then what we have now, if you think of the lim of X, goes to 0 from the positive side. If you just take X, a function log X of X, you know that this one is actually equal to 0. So what I'm doing now is simply I'm replacing P of X with a variable X. So instead of writing P of X here, I just wrote X. And we have this limit, so that means that this divergence, since it's also a log, is a concave function. A probability can never be negative. It doesn't make sense to have a negative probability. I don't know what it means. So that means that this quantity, this dkl, is a quantity which is always larger or equal to 0. So that means, again, that if you now look at what we had in the equations, we go back now, you see that the first term is actually this Kullback-Leibler divergence. So that means that what we can do then, we can rewrite this optimization part, log P of X can then be rewritten in terms of this Kullback-Leibler divergence, Q of P, for these probabilities Q and P, minus, and P of X now is not our true probability. This P of X is actually the model which we want to make. This is the one we are going to optimize. Minus this reconstruction error, which I just write like this, reconstruction plus some constants. Now, the reconstruction error is also going to be a quantity which we obviously want to be equal to 0, but it's going to be a quantity which will be either 0 or larger than 0. And the Kullback-Leibler divergence is also a quantity which will be equal to or larger than 0. So that means that this function, when we're going to optimize it, is going to set up a lower bound for the optimization. So this is actually something which is pretty beneficial. And what we're going to do now is to simply to bake in all the other terms. But let's so let's go back a little bit now and bring in the full probability distribution. So let's set up what we actually want here. So in our case, for us, we are going to have the following. So we want a probability distribution, P of X of theta. This is the one we want to generate the data, X tilde, which we then want to compare with the input data. And I'm going to simplify the notation a little bit. So I'm just going to call this P of theta of X. So that's my final one. Then this is the quantity we want to optimize. So we want to optimize log of P of theta of X. And this is the same as setting up log, and then we have the integral over P theta, and I write it like this. So I put in the explicit theta dependence times P theta of H multiplied with D of H, like that. So keep in mind now that what I'm doing is to look at the final part of the decoder. So this is a quantity I want to optimize, which means that if you now look back at the figure which we put up, this is going to look like as follows. So take a closer look at the term here. So this one, this is, if we now go back to the figure which we put up before the break, this figure here, this is the part which starts with the latent space, P of theta. It has a decoder part here. And then when I integrate over all the latent degrees of freedom, I'm going to get the final probabilities P of theta. So what I've done here is to set up this part, which brings us to X tilde. So the variables which I plugged in, which you see here, are the variables from the right-hand part of that figure. And you see that everything has a label theta here. Then we are going to assume the following. If we do that, we are going to assume that there is a latent space whose distribution links the input data distribution, which I'm going to call for Q of phi of H of X, links the input data with the latent space H. Like that. So although the parameter phi is hidden for us, because this distribution will also have parameters phi. So if we now go back to the image which we made, I'm going a little bit back and forth here. If you look at this image and think in terms of an autoencoder. So when you have an autoencoder, you don't have probabilities. But with an autoencoder, this would now be a neural network with its parameters phi. That neural network transforms your data to a smaller dimensionality, which then defines the latent space. Now, from the latent space, we then have a decoder part, which reconstructs the value X tilde, then through a new function. So if you look at this image here, and we go back to where we started in the lecture, this image here, this is a decoder part, except that now, instead of having this is typical a neural network, this can be a neural network. So instead of using a neural network, we are trying now to train a probability. And the parameters phi are going to represent that probability. And the parameters theta are also going to represent the probabilities we are interested in. But you see clearly that, like when you run this in a neural network way of doing it, then you have the parameters of the neural network and you fix everything, and then you run the calculations. Then you can increase the neural network, you can make it deeper and deeper until this reconstruction error goes to zero or becomes as small as you can accept. The difference now is that we are going to train probability distributions to actually perform this encoding part and the decoding part. So when we split this integral, as you saw with a Kullback-Leibler divergence and the reconstruction error, we have a lower bound for what we should get. And that lower bound allows us to vary the parameters, so we have a variational approach to it. So this has normally been called a variational method to a neural network or to a network, or variational Bayesian methods. But then variational autoencoder is a name which I actually like because it mimics a lot of what autoencoders are doing. Any questions so far? Does that sound okay? So the part which we are going to deal with now is, because in the equation which we put up, in this expression which we have here, this one, we don't have the variable phi, because the type of optimization we want to make is obviously this one. So we want to find an optimal theta, we want to find an optimal phi, and that is going to be given, since we are now optimizing a log function. This is a maximization problem because the function is concave. If I do minus log, then I have a convex optimization problem, then I have an argmin. So I'm going to optimize this one with respect to that. And I have my log, and then I call it pi theta of x, and I'm suppressing phi here, because phi is something which I will bring in now. So this is going to be given by log, and then I have this integral over p of theta of x of h of d of h. It's the marginal probability which I want. And then I'm going to use the product rule, and I will rewrite this one. So this one is obviously equal to, just let's wait a little bit so everybody can write what is needed to write. So if I do that, then this is nothing but log, and then I put a parenthesis, and then I have a d of h, and then I have a p of x of theta of h, and then I have a p of theta of h. And then I'm going to put in a 1 here. So insert 1. But now this is going to be given by this quantity which I have here. Like that. So now I'm introducing this probability, which is part of the decoder. If I do that, then I can then use, so what I get then is just log, and then I have the integral, and then I have a p of theta of x of h. This is actually x, h, like this. And then I get a q of phi of h of x, and then I have a p of theta of h of q of phi of h of x, and dh. Now I can then I can actually show in the same way as we did before, that using Jensen's inequality, then I can show that this one is going to be larger or equal than, so this will be larger and equal than the expectation value. Because if you look at the term which I have here, I can actually rewrite this in terms of expectation values. And it's going to be given by the expectation value of h which now follows this distribution Q of phi. So as a parenthesis, H is going to follow Q of phi of H of X, like that. And we are going to have an expectation value of log of P theta. And then I will have P theta. Let me see now, did I write this correctly? Let me just check that I actually wrote it correctly. Yeah, this is P theta of X of H. That is one expectation value. And then plus E of H following Q of phi. So this is another expectation value. And this will be the expectation value of log of P of theta of H divided by Q of phi of H of X. Like that. Now, the last quantity which you have is nothing but this Kullback-Leibler divergence. So we can actually write this out as an expectation value of H given Q of phi, generated according to that probability, of log of P of theta of X of H, like this. Now, this part which you see is a part which I'm going to single out here, this one. This is nothing but what we called the reconstruction error earlier. And this term, which you see here, let me single that one out. This P of theta, this is the decoder. This is going, if I now assume that this term here looks like a Gaussian, then I can actually rewrite this exactly in terms of the standard reconstruction error. But this term is the one which if we look at the simpler case we had before the break, is something which is just going to give us this reconstruction error. Then we are going to rewrite the second term, since I'm going to interchange Q. So we're going to have a minus instead of plus, because I interchange the definition of the distribution. So I'm going to have a minus of the Kullback-Leibler divergence, KL, of this Q of phi of H of X, and then this is now being tested against the P of theta of H. So these are also terms which we are going to optimize. So this term which we have defined here, this one, this is our encoder. So what is common to do now? So when we are going to implement this numerically, the encoder part of the variational autoencoder is normally commonly chosen to be a multivariate Gaussian. So that means that if we know this term here in terms of a Gaussian, and if we assume that this one is also given by a Gaussian, then we can calculate that integral analytically. And that is a common approximation which is made. So we are going now to look at these type of approximations. So the approximations which are often made because then the final term, the reconstruction error, is something which we will use in the optimization here. And where we will actually have to calculate a expectation value using Markov chain Monte Carlo methods. So it's pretty common to assume in this part here, you will have parameters, theta and phi, but you're going to assume that it has a specific shape. if you have a specific shape, you can calculate that integral analytically. And this is a common practice, which you will also see when we move into diffusion models. Because at some point, if you want to evaluate these lovely equations, you have to make some approximations. So what we end up with then is to train a probability distribution where we optimize the parameters theta and phi of two expressions, two integrals, so that when we take the gradients here, we hopefully find the best possible parameters theta and phi. So the kind of standard approximation in all of these methods is that this one, q of phi of h of x, is then given by a normal distribution, which depends on h. It depends on some mean value, which we have not defined yet. So we are coming back to that next time we meet, because then we need to discuss actually how we do this parametrization. Okay, so now we're just going to set up the equations which are needed. And then after the Easter break, we're going to see how we can encode it and what kind of approximations we're going to make in order to set up the mu values. But we will also have a sigma phi, which will depend on x. And these are parameters which will enter that one. So there will be parameters here for the mean value, and there will be parameters phi in the standard deviation. Okay? Then, what is also common, the next approximation is to take P of h, P of theta of h, and we set that one equal to a normal distribution, which depends on h. So h is generated by a normal distribution, but where now the mean value is 0. So this is simply a standard normal distribution centered around 0, and with a variance which is equal to 1. So this quantity which you see here is a multivariate Gaussian, so it can depend on many variables. And the P of theta is normally assumed to be a plain normal distribution. Now with that, then we can calculate this Kullback-Leibler divergence. We can calculate that one analytically. So that means that when we look at the calculations now, we can then evaluate the DKL divergence analytically. So the optimization part, which we need to set up then, our max here, for theta and phi, is now going to be given by this function here, which we want to optimize. We want to optimize an expectation value where we have q of phi. Oh, sorry, let me write it correctly here, where h follows q of phi. And we are going to calculate the expectation value of log of p theta of x of h. This is an expectation value, minus this Kullback-Leibler divergence, which we can evaluate analytically, of q of phi of h of x of p of theta of h, like this and like that. So this is commonly evaluated analytically, but it will depend on the parameters theta and phi, obviously. Analytical evaluation. This part here is done by a standard Markov chain Monte Carlo sampling. And typically you would then use something like a Gibbs sampling or other ways of sampling the points and accepting the points when you're calculating that specific expectation value. But keep in mind now that the h's which are going to be generated they will be functions of this probability Q of phi, which we have defined. So the aim today was to set up the equations. And when you then do the optimization, it means that we have to calculate the gradients of these quantities. So we haven't discussed that yet. So the whole idea of the next lecture is that we are going to look at the practical implementations and what kind of approaches are needed in order to write our own code for a variational autoencoder. But these are essentially the equations which we want to encode, and the optimization is then done with us setting up a model for Q of phi and a model for P of theta. What we have not discussed now is how we define these mean values and how we define these variances. And this is something we will discuss in more detail next week. So the theory here is a lookalike of what we did with Boltzmann machines, but it gets a little bit more involved now because we are training a probability distribution. And the probability distribution we want to train is obviously the quantity which we put up here. This is the quantity we want to find, or rather this one, because that's the final product which we then will compare or use to generate the new points, which we then compare with X0. Okay, so this is essentially the strategy of variational autoencoder. And at the end, we will then have a probability distribution P of theta, which you then can use to generate, let's say, new images. So today I wanted to give you the kind of overarching view and link it with Boltzmann machines. And at the same time, I wanted to keep in mind that these variational autoencoders are kind of stepping stones towards the more popular diffusion models. Okay, I'm going to stop here. And then I'm going to wish you all the very best